Breaking news. At precisely 0218 UTC this morning, a routine observation window assigned to the Hubble Space Telescope delivered data that no one on the team was prepared to see. An interstellar object, catalogued as 3I Atlas and believed to be largely inert, suddenly revealed structured jets, rotational motion, and compositional signatures that defy every established model of cometary physics. Moments ago, alerts rippled through mission control centers on 3 continents. Engineers froze live data feeds, scientists rechecked calibrations, and then, quietly, one realization settled over the room. Today, the impossible just happened. What was once assumed to be a fading interstellar visitor is now behaving like an active, controlled system. This changes everything we thought we knew about objects beyond our solar system. If you want continuous updates as this story unfolds, make sure to like, subscribe, and stay with us, because what we're witnessing may be the most important astronomical discovery of our lifetime. Within minutes of the first anomaly, verification protocols were activated across the global astronomy network. NASA's Goddard Space Flight Center confirmed the integrity of Hubble's Wide Field Camera 3. The European Space Agency cross-referenced the data stream through its European Space Network ground stations in Spain and Australia. At the same time, independent observatories, Caltech's Palomar Observatory in California, the Atacama Large Millimeter Array in Chile, and optical arrays in the Canary Islands were instructed to pivot their instruments toward the same coordinates. Across North America, South America, and Europe, the same conclusion emerged. The jets were real, the rotation was measurable, and the composition data did not match any known class of natural comet. Before we go any further, it's important to establish credibility. These observations are not speculative. They come from the most advanced instruments humanity has ever placed above Earth's atmosphere, supported by decades of peer-reviewed physics and verified by multiple independent teams. To understand why this moment is so extraordinary, we need to rewind the clock. 48 hours before Hubble's detection, 3I Atlas was considered unremarkable by interstellar standards. Its heliocentric distance measured 3.7 astronomical units, well beyond the region where solar heating typically drives cometary activity. Its apparent magnitude suggested a cold, dormant body. Gravitational models predicted a smooth, passive trajectory. No thrust, no torque, no surprises. Then, 11 hours before the event, a minor deviation appeared in tracking data from the European Space Network. The object's velocity vector shifted by just 0.04 kilometers per second. Normally, such a discrepancy would be attributed to solar radiation pressure or data noise, but when the shift persisted across multiple measurements, analysts flagged it for review. 6 hours later, Hubble's ultraviolet spectrograph recorded something unprecedented. A narrow plume, barely detectable at first, extended from the object's surface. Within 90 minutes, that plume resolved into multiple jets, each emerging from distinct points and maintaining consistent angles relative to the object's rotation axis. These jets were not chaotic, they were symmetrical. Their emission velocity averaged 1.2 kilometers per second, and their temperature exceeded 1100 Kelvin, far too hot for sublimating water ice at that distance from the sun. Even more troubling, the jets pulsed. Every 73 seconds, emission intensity peaked, then fell, then rose again, like a heartbeat measured in photons. As data accumulated, a second anomaly emerged. 3I Atlas was rotating, and not randomly. Spectral Doppler shifts revealed a rotation period of exactly 8.64 hours, stable to within 1,000th of a second. Natural bodies rarely exhibit such precision. Gravitational torques, outgassing asymmetries, and internal heterogeneity introduce noise. But here, the rotation was smooth, controlled, and unchanging. No natural process could produce such stability under these conditions. As one analyst quietly noted in the control room, this isn't tumbling, it's spinning on purpose. The composition data deepened the mystery. Infrared spectroscopy identified carbon monoxide and molecular nitrogen, expected in interstellar objects, but also detected complex organics arranged in narrow spectral bands. Some of these bands corresponded to long-chain hydrocarbons that require controlled formation environments. Others did not match any cataloged natural compound. Most unsettling of all was the absence of water vapor. Traditional comets erupt with water-based jets when heated. 3I Atlas did not. Its jets were dry, energetic, and precise. At this point, scientific investigation intensified. Dr. Elaine Mercer, a computational astrophysicist at Harvard, led a rapid response simulation team. Using gravitational modeling and jet force vectors, her group attempted to reproduce the observed motion using known physics. The results were unequivocal. Even under extreme assumptions, exotic ices, unusual internal structures, the models failed. The simulated object either fragmented or deviated wildly from the observed trajectory. Meanwhile, at Caltech, Dr. Raphael Nguyen analyzed polarization data from the jets. His conclusion was equally stark. The emitted material showed alignment at the molecular level, suggesting directional control during ejection.
Composed of ultra-volatile materials that activate at lower solar flux. Proponents argue that the jets could be driven by phase transitions in exotic compounds and the rotation stabilized by an unusually uniform internal mass distribution. It's a cautious theory, grounded in the idea that nature still holds surprises, but it struggles to explain the precision of the pulses, the absence of water, and the consistency of the rotation. The alternative hypothesis is more controversial. It suggests that at least some of the observed behavior is technological in nature or driven by unknown physics beyond our current understanding. In closed-door meetings, some researchers have noted that the jet timing aligns with prime number intervals when corrected for relativistic effects. Others point out that the jets activate only when the object's orientation relative to the sun reaches specific angles, as if responding to an external reference frame. This was no longer random, it was responding. Then came the second wave of anomalies. 12 hours after the initial jet detection, one of the emission points simply vanished. No explosion, no debris. It disappeared from optical, infrared, and radio sensors simultaneously. At the same moment, the remaining jets adjusted their angles, compensating for the loss. The object's rotation rate did not change. Energy output remained constant. Conservation laws were maintained, but only because something actively corrected the system. Within minutes, Hubble recorded a brief radio emission, a narrow-band signal at 4.2 gigahertz, repeating in a sequence of pulses separated by intervals of 2, 3, 5, and 7 seconds. Around the world, reaction was swift and muted. At NASA headquarters, internal memos instructed teams to classify certain datasets. ESA issued a carefully worded statement emphasizing ongoing analysis. GEA agencies convened emergency science briefings. No alarms were sounded, no public warnings issued, but behind closed doors, the tone was different. This was not panic, it was focus, the kind of focus reserved for events that rewrite textbooks. Subtle effects were noted closer to home. Low Earth orbit satellites reported transient signal noise during the radio pulses. Magnetometers detected fluctuations of a few nanotesla, small but global. In the southern hemisphere, radio astronomers reported brief blackouts at frequencies matching the emission from 3I Atlas. Individually, these events meant little. Together, they formed a pattern. And then, abruptly, the jets stopped. For 16 minutes, 3I Atlas was silent. No emissions, no pulses, just a rotating object against the star field. Some scientists believed the activity was over, that whatever process had driven the jets had exhausted itself. Others waited. At exactly 1904 UTC, the jets reignited, but differently. Fewer in number, higher energy, perfectly synchronized. The rotation rate shifted by precisely 0.01%, settling into a new stable state. It was as if the object had adjusted its configuration. In moments like this, science becomes philosophy. We are forced to confront the limits of our assumptions. For centuries, we believed the universe was silent, indifferent, governed by blind forces. But now, an object from another solar system displays behavior that looks deliberate. Not hostile, not friendly, simply precise. Maybe we're not witnessing the end, but an invitation to expand our understanding of what is possible. As I look back at the data feed from that first detection, one thought keeps returning. We are not the center of the cosmic story. We never were. And yet, for the first time, the story may be aware of us. The jets, the rotation, the composition, they tell us that 3I Atlas is not just passing through, it is doing something, and we don't yet know why. The final images from Hubble, transmitted just minutes ago, show the object rotating calmly, jets dimmed but poised, like a system waiting for its next command. The question now is not whether this object is unusual, that much is certain. The question is what happens next. What happens when the jets activate again? What happens if the rotation changes once more? And what happens if this behavior is not unique? Subscribe to stay with us as this unprecedented investigation continues, because the story of 3I Atlas is far from over, and the next update may change our understanding of the universe forever.